Good morning. Today we will be presenting our Civil 30 Excel project. My name is Timothy Farrance, and I am accompanied by Jordan Beatty, J.S. Young, and Lucas Bilow. Today I will be explaining the site information part of our Excel. This is the area in which we can calculate our live loads as per OBC and our snow loads as per OBC. If you look over here, you will see will snow load contribute? We can check yes or no. In this case, we would like 1. We will select the location of the beam. For today, we are looking at Kingston, Ontario. Now we will be asked, what is the use of the building? For the purposes of today, I believe we're going to stick with classroom. And the importance factor will be normal. Our roof slope will be a flat roof, so it will be less than 30 degrees. We are not exposed to chlorides. And the length of the beam will be 8 meters. We will have a tributary width of 5 meters and a 150 millimeter roof slab. We will not add additional materials for the roof, but if we were to, we could do it here. Our mechanical allowance would be 0.5 kPa, and our overall roof UDL, due to stuff magically supported on the roof, would be 5 kPa. We won't be adding an additional point load, but if we were to, we would enter the amount of the point load and the distance from the left of the beam and the distance from the right of the beam. That can be shown in this diagram over here. Finally, we will just type in a wind load. If we knew the wind load, we would just put it in. Today, we're going to go with 2.5 kPa. And that concludes the site information section of our Excel.
Okay, hello. Just to continue off of what Tim was saying about the climatic data and the other live loads, I'm going to run you through the material information. So as you can see here, you can enter your compressive strength of concrete. It's set at 35 now. I'll change it to 45 just for the purposes of this demonstration. Density of concrete at 2,350 kilograms per meters cubed. Through the drop down here, you can choose whether or not your concrete is cast in place or precast, and your strength of steel at 400. I'll change it to 300 MPa again for the purposes of this. And your EC and your N values are calculated based on your previous choices. You can find that information in the calculations tab. After that, you can go down, and in your reinforcing steel section here, you can see your minimum area of steel, your area of steel, and then you can choose your bar designation as well. Thank you.
Hi there, my name is Jean-Sébastien Young, and I'll be continuing off of what Tim said and Jimmy said. So as you can see here, we have our site information, which Tim has previously entered for us. It's all presented nicely in a neat fashion in order for easy read. So is also the live loads and snow loads that you also entered. They're found in here. The reinforcing steel and other material properties are found here. This is what Jimmy entered earlier. And as you can see, it summarizes all the information, all the calculations of the previous sheets within this Excel sheet, spreadsheet. Here are the shears. This will be explained later on, or early on. Here are the moments for UDL, unfactored, and factored. Here are the dimensions for the beam, height, space, cover, spacing. None of these numbers are calculated on this page. All the values found on this summary sheet are done in the calculation page here. The second summary sheet is essentially just a visual guide to represent what is going on with the beam and where certain elements or materials are located, such as the bar size, where the ties are, bar spacing, and all that good stuff. Here's also an image of the shear planes. This is where the ties would be located if this was a profile view of our beam. As you can see, we have 3 ties. The tie spacing is 1,000 millimeters, and the cutoff location is about 2.8 meters. Yeah, let's continue off with Lucas.
Merry Christmas, Daryl. All right, I'm going to start with going through an example after the 3 gentlemen have already gone through explaining the site information, the material information, along with the reinforcing steel. And JS is explaining the summary sheets, how they've been designed to be something presented for your boss. So what I'm going to go through is go through an example. We have it set up the way our first test was set up. When saying a snow load will contribute, we have it set up for going through in Windsor, and we have it selected for a roof. That's how we had the test set up there with the a beam with a length of 11 meters and a trib width of 4.5 meters. We used a floor slab was recommended of 150. We've left the other material information empty as per the question. Again, as Tim said earlier, it's something you could input as well. So with that information inputted there, we'll go to the actual material information that was already inputted from Jimmy, and we can see that the compressive strength of the concrete together was 35. We go through, we made the options available to drop down. So I'm going to begin going into more of the beam sizing and dimensions. So we have it set up that our beam size would be looking at the calculation that we had before. That would be the value of the length of the concrete divided by 16. That would give you a recommended value. This allows you to enter a desired moment in, or desired height of the beam. And we have it set up that the calculations, or that the calculations will set up that will show you that deflection check has either been not required or not met, and that is what that calculation is set up there. And we have left it so you can still desire the information to put the number in that you request, as well as the base, the cover, and the spacing. We have the cover set up to represent what was in the code in regards to the cover that is required for each situation. If you go back up to where we are exposed, not exposed, exposed to freeze, exposed to chloride, and exposed to earth, we have the cover set up to cover that would show the dimensions that would be required to meet the requirement of the code. You can still enter it in. If you enter a value in that's less than that, you can see that it will get an error message there to retry, telling you to try it again because we need it to be above that. If you go again back up to the height and the deflection, if you go something below that, you'll see that it will fail on that instance there. So we have it set up letting you know if you'll fail in any circumstance as well. The spacing again is calculated with the different bars designation and size, again with every other calculations involved, but it'll tell you the minimum spacing required. This is not something you can enter. It tells you what your spacing is, and it's telling you the minimum required that is there. We have it set up so that it'll calculate your D value, of course, and then your C values. C values for both cracked and uncracked, and then we have it be able to populate the moment of inertia of uncracked and cracked, which we need further to designate the shear and the moment factor. As Tim was showing earlier, we have the load set up as well, with every load populated here with what you entered up below, and then we have it having it be able to calculate through our calculation sheets through this section here that will show you, that will go through, and then it'll determine which load case is higher and populate it here and give you the actual load case that it is and the factored and unfactored moment that is there. If you're doing a point load, it would also be populated there as well with factored and unfactored, and again, taking into consideration the governing load case. When we start looking into the reinforcing steel that Jimmy was talking about earlier, we can see that it allows you to input the type of bars and the number of bars. With that information, again, you'll be able to control when you're designing, basically when you're using the sheet, being able to manipulate the bars, the number of bars and the type of bars will allow you to pass your moment resistance. As you can see, if we drop down the moment bars to something like a 10 millimeter bar, you can see that our moment resistance fails. Along with that, our moment resistance is less than our cracking moment. So this allows you to have some customization when you're actually doing the sheet or when you're designing your beam. If you want to make it as economically as possible, you try to make your moment resistance as close as possible to your total factored moment. As you can see, we have our factored moments with their point load factors all in here. They contribute, and this is our number. This is our total factored load in this location here, and this is our moment resistance. So you can see we're very close here. So we're trying to just get this limit just to past it. As you can see, we have it set past there. Our crack control again is controlled. Everything is calculated through our calculations, but as you can see, when you increase the cover limit and things like that, the crack control will expand and decrease. So as you can see, everything you do, everything is interactive. If you change something on this sheet, it will change it and it will tell you if it passes and fails. We'll start to look at the shear. Now the shear again is calculated again according to our regular methods. We have it so it tells you that if your shear resistance will pass without the ties, and we have it with it if it does pass with the ties. When we've done through majority of our trial runs, most of our trial runs, and we understand those are the main reason why we didn't do shear resistance without having the shear ties in it, we saw that majority of the time it fails. So you have the option again to add it. It tells you if it fails with it and without it, but you can add the ties in and have the ability to add the type of tie. Along with this, it tells you again whether it passes or not. It allows you to be able to put the shear tie spacing in, and this will have it again an impact on the shear resistance with ties. As you can see here, when I change this one column, the other column will change as there, and we have the ability to let us know that where the location of the shear tie cutoff is, and that is again all calculated based on our calculations that we've learned in class. So as we can see, we've gone through the whole entire thing, inputting what we'd like from the test. When we're looking for a test example like this with our things, we can see the way we've set it up with 630 M bars. We can see it totally passes in this circumstance. So we can see that basically our sheet is able to be designed for any sort of environmental circumstance, any location, and allow you the ability to be able to select bars and number of bars to build a more economical option instead of just providing like that there. Once all your passes pass, as you can see, all your green passes with your shear resistance with ties, your moment resistant passes, your crack control passes, your steel, and as your cover and everything meets, you can then have your summary sheet, which will display everything like JS said there, and you can print that out, and that can be displayed to your boss, and that'll show it. So Daryl, this is our beam design calculator from Lucas, Tim, Jordan, and JS, and we thank you so much, and Merry Christmas.